Good afternoon. Good afternoon. Right, today I want to talk to you about how to achieve OpenStack high availability and reliability. The aim of this talk really is to look at, is high availability really that hard? So when crafting up this presentation, I was thinking of, well, what could the presentation also be called? It could also be called high availability and reliability for something simple called OpenStack. Or it could be, I don't see why OpenStack HA and reliability should be hard. So what does OpenStack offer? Quite basic, flexible compute, storage, networking. What else? Instantly available, scalable resources. That's great. It's on-demand, right matching resources between availability and requirement. And with this, there is expectations that it should just work. It should be just like magic, right? And let's delve a little bit further. With cloud, we have new roles around the operator versus the consumer. So the operator versus service consumer. The operator's role really is to drive the underlying infrastructure. Operate the underlying infrastructure, get it up to the point where it provides the virtualized resources, and it stops at that. Nothing more. The operator doesn't get into the workload, doesn't get into what happens inside the virtualized environment. On the other hand, the consumer doesn't care about what happens in the underlying infrastructure. Just want to use the resources, and that's it. It's only responsible for whatever that is running inside the environment. And as far as the consumer is concerned, he's only consuming the resources. And so therefore, the system should, as far as the consumer is concerned, should be just work. So this means that the operator has a responsibility to keep this thing up and running at all times. If that's the case, then when the expectations are not met, then we see that it's a death situation. Service is dead. But if it's dead, it's too late because the services are impacted and service consumer is impacted, and somebody's not going to be happy, right? So when can there be risk of death? This is a very dark talk. I'm going to be talking about death a lot. Now, let's take OpenStack lifecycle, break it down into 3 parts, and let's look at death in each of those 3 parts. So OpenStack lifecycle, you've got deploy, operate, and upgrade. In the deploy phase, yeah, it can be challenged. And yes, if you screw it up, it will come back and bite you. But you may not necessarily know that you screwed up until sometime later. That's a problem. And if we look at the operate phase, what do you want? You just want to keep the services running. And so therefore, HA isn't a luxury. So what's the risk of death? It's when the services are encountering problems and impacting the service consumers. If we look at upgrade, we've got two options for upgrades. Either we do 2n upgrades over n years, or we do 2n upgrades once in n years. Take a pick. So the risk of death is really downtimes and interruptions during upgrades, and worse, if any workload's killed. I was talking to a relatively prominent research site, which shall remain nameless. When they talked about upgrade, they said, well, we currently have one cluster. For upgrade purposes, we're going to stand up a second cluster, kill all the VMs on the first cluster, and tell the users to start the VMs on the second cluster. Sounds like a joke, yeah? Except it's reality. And this is supposedly smart kids. So if we then look at risk of death, the key risks are essentially in the operate and upgrade phases. In upgrade phase, what you really want is zero downtime. Minimize downtime, at least. And here, this is where a solution architecture that you put in place way, way, way back in deploy phase, that has to enable it to meet the requirements. Otherwise, you'll be discovering at upgrade phase, damn, we have problems. Now, if we then switch to looking at death during upgrade phase, we've got two types of risks: intrinsic risk and extrinsic risk. What about extrinsic death risk? Extrinsic death risk, this is external to OpenStack, as in it is not due to anything inside OpenStack itself. The cause isn't originating from within OpenStack itself. So this, you can deal with it with a traditional HA solution architecture. Now, what's OpenStack? Just a bunch of intercommunicating services talking through HTTP, MQ. Anything else? Come on, you guys know this stuff. Anything else? Did I miss anything there? Databases, right. Anything else? No? Only databases. So, if we look at types of services, we can further break them down into services that have data and configuration, and services that are configuration only, so effectively stateless. So, for configuration, so long as we can operate the system in an infrastructure as code model, then we should be all right. There's no data, so we can just simply redeploy if there are any problems. You messed up? Fine, no problem. Kill it, redeploy. It should be automated. What if there's data? If there's data, then we don't have any other choice, right? Replicate, replicate, replicate. And we'll either do the two-node model or the quorum odd node model. Any other models? No? So, for safeguards for data, traditional HA operations model. Anything else? Well, for the web servers, they are just talking HTTP, right? Much of OpenStack services, they are just talking HTTP. So let's treat them as web servers. As for MQ, the principle behind MQ is you put stuff in, you get stuff out. So therefore, replicate the readers and the writers. So for extrinsic risk, we therefore keep an extra copy at all times. That's the core principle. Is that all? Yep. Smart. It's a solution architecture. You get it right, it's good. You screw it up, it'll come back and bite you. What about intrinsic death risk? This is where it starts to get interesting. It's intrinsic. It's not external. So the traditional operation model, whereby you're monitoring, and then upon some condition, you trigger an alert, you then take some action. But monitoring, what you're really doing is you're looking for dead or alive. If it looks dead, because you're sending probes, is it alive? Is it alive? Is it alive? It's not responding. Let's check 3 times. Oh yeah, it is really dead. But if that happens, it's too late. It's dead. When it's dead, service consumers are already affected. This is not good. So for intrinsic risks, the traditional HA model will not suffice. So what do we need to do? We need to look at 6 states. When something is sick, it is not healthy, but it's alive. And to be able to do this, we also need to correlate between certain X and Y. We're not looking for straight causality. Causality, that's an easy one. A causes B, and you can trace the causality chain. That's easy. Many of you have seen this picture. So this shouldn't be news, right? And with that, you want to work out causality versus correlation? That should be fun, isn't it? So this need to work out the 6 states becomes a non-trivial computational task. Plus, what's sick in one environment is not necessarily considered to be sick in another environment. This is like if you're looking at patients, certain situations, the patients could be deemed to be sick, and sometimes the doctor says, it's perfectly fine, go home. So, but to drive that, we need data. What kind of data are we looking at? We've got 2 types of data, metrics data and log data. And it needs to, for example, take the response time behavior of a certain web app, certain web service, fuse it together with some smart errors from disks. And then with that, you would be able to detect 6 states that are below radar. Because if you set your smart errors threshold at, let's say, 3 times an hour, then your traditional monitoring would look for, has it hit the threshold? It hasn't. So it's not going to make any noise about it, and just keeps running. And some point in time later, kaboom, the whole thing goes. Just because it's below the radar, you haven't caught it from your monitoring. So how do we do it? Well, you take OpenStack infrastructure logs, you shove it in to a time series data store, and you watch for anomalies. So the analogous situation is where, for example, you have a bunch of patients, and you line the patients up. And let's suppose that the patients are actually alive, because if they are already dead, you can eliminate them, right? So the patients are alive. Let's line them up, shove them into the X-ray machine, and you take pictures of the patients. And then you take the pictures, you shove them through a decision engine. With that, you detect if the patient is deemed to be healthy or sick. So, for example, you detect certain dark spots, and you consider that to be sick. But note that for the decision engine, it doesn't care whether the picture is a picture of the patient's chest or combination of head and foot. It doesn't matter. And if the decision engine gets it wrong, you need to be able to retrain it. So the next time, dark spots could be flagged as the alternate state, whether it's from healthy to sickness, or vice versa. And we also need this thing to be configurable in terms of what are the constituents of the picture. So in other words, whether it's the head, foot, and the palm. And it needs to be configurable in its time window. And then allow the operator to trigger retraining on certain wrong decisions. Computationally, we know that this is non-trivial. But there are certain shortcuts that we can take. We know that as a precondition, the service needs to be alive for us to check if it is sick or not. And then we can further leverage a causality relationship to help cut down our search tree. And obviously, we're running a system here that is a non-toy system. So HA for a decision engine, it's a must, not optional. So we've got a question. How do we build HA for decision engines? How do we build HA in a manner that you're not going to get multiple triggers and you're going to get the same decision from multiple evaluators? And we also need this thing to be able to operate on stream data, so no polling, because polling, you're going to hit limits. And we need it to be able to handle back pressure sensitive so as to not overload the data pipeline. And as you scale up the system, you're going to get to a point where even the fastest single box that you can get from your hardware vendor is not going to suffice to run the number of evaluations that you need to do. So for the system, we therefore need to build a solution for the evaluation to be balanced between multiple nodes quite simply. So ideal situation would be, well, if it's not fast enough, ring up hardware vendor. When the server arrives, plug the server in, rerun our deployer, because this thing is stateless, rerun deployer, bang, the whole thing rebalances itself. That's what we should aim for. And as I mentioned, HA for an evaluation system, non-trivial stuff. But if you look at data, how much data are we looking at? If we're looking at 4 bytes per metric, and we've got 24 cores a node, which is not extreme, and we've got 4 VMs per core, again, not too crazy. And if we have 200 plus metrics per VM, and if we do this per second, that works out to be 44 gigabytes a second. That's just for the data, from metrics data. That's a shitload of data. What about logs? Logs is a little bit easier. If you have 256 bytes per entry, and you get 1 entry per second and 80 plus services, that only works out to be 72 gigs per hour. It's quite easily manageable. So, smarts, we need to know what to ingest, how to reduce the data ingestion. As well, once we've taken the data in, we have this pattern whereby you have got lots of small writes, but when you're reading out, you have small number of very large reads, because these are aggregated reads. And that pattern isn't well satisfied by many of the time series databases in the market today. But if we can deal with these problems, we would know of imminent fault. We can deal with threat while it's latent before it becomes patent. And deal with consumer expectations, we can meet consumer expectations, and most critically, we can avert death. In other parts of the life cycle, we've got various other challenges, like, well, for deployment, really what we want to do is we just want to get this thing up and running easily and flexibly. How many of you dealt with Linux in 1997? How many of you? A few hands I see. Now, if you were to ring up a hardware vendor in 1997, and you tell a hardware vendor, hey, Mr. Hardware Vendor, I want Linux on my servers, what would the vendor say? Sorry? Yep. Or it'll tell you all sorts of different things, but inevitably, it comes down to no. Fast forward to 2017, you ring up a hardware vendor and you say, hey, Mr. Hardware Vendor, I want Linux on my servers. What would he say? Which one? When? How much? What's happened between 1997 and 2017 in relation to Linux? Automation. Automation to the point where the guy in the factory who doesn't even know what the hell is Linux can get it deployed. My question is, can we do the same with OpenStack? If the argument is no, then my question is, why not? Throughout the OpenStack lifecycle, there are a number of other challenges. For example, in resource management, OpenStack, when it comes to resource management, is not terribly smart. I'm telling you guys, as folks who are thoroughly familiar with OpenStack, right? There's still a lot to improve in resource management. For example, how many of you have around, let's say, 4 to 8 cores on your laptops? Practically all of you, right? And when you guys run PSAUX, pipe to WC minus L, how many of you have a result of less than 8? Practically none of you, right? What happens on the machine? Somehow, some way, each of the processes are given time on the CPU. And when you switch, when you first start an application, whatever the application is on your laptop, do you tell the kernel that, hey, kernel, I want 2 gigs of memory, and I want 1 core? Do you tell your kernel that? In most situations, you don't. So, and when you are switching between applications, you just switch between applications, right? Do we manage resources the same way in OpenStack? Considering that from the host point of view, a VM is just a process like any other. So why on earth are we still pinning 1 core, 1 VM? Or if you're doing overcommitment, you're essentially doing the same thing. Still, percent of a core to a VM. Is that a smart thing to do? That's my question. As for the deployment, I've touched on this a little earlier. What we should get to is from 0 to showtime in 1 cup of coffee. Can we do that? How many of you have done that? Anybody? No. Wow. I've touched on just to expand further on resource management. There's tremendous impact on CapEx and OpEx if we can manage resources in a dynamic manner. Because the moment that we get away from this rigidity of however many cores to however many VMs, you can really run your facility in a high elastic manner so that when you have greater load, you bring up more machines. When you no longer have these nodes, you shrink them down. Typical bank, some of the applications, they run for 8 hours a day, which means 2/3 of the day, you could be essentially running a glorified heater. Not a good thing. That's topics for another day. This is Sardina Systems. We run business developing AI-driven smarts for automation within OpenStack, one of OpenStack corporate sponsors. Some of our customers are in finance, government, aerospace, and a couple of years ago, we won the IDC HPC Innovation Award. The system is in production in sites including a top 10 trader on the New York market. And at University of Edinburgh, we run the university-wide private cloud. At a classified government site where I used to run as a single region, 150,000 VMs. And that particular customer, one of the things that they said on day 0 of engagement with us is that this thing, there's no POC. There's no trial. You got one shot, and it needs to work. My name is Kenneth Tan. My contact details are on there. Any questions?
Can you introduce some best practice or common tools you use for the HA stuff in OpenStack?
So tools for HA.
Yeah.
So first off, if you're looking at databases, make sure you run 3 nodes. Write anywhere 3 nodes. That's your starting point. And then essentially, you take your facility, you break it down into 2 halves. Look at it as left and right, the simplest. And HA proxy on top with VIP and VRRP between them.
Do you use pacemaker?
Keep alive D.
Keep live D.
Yeah.
So everything using HA proxy, talking to every API service?
Yeah. And when it comes to upgrade, essentially you kill 1 half, upgrade the left, you bring it up, kill the right, and upgrade the right.
All the cluster like MySQL or are they all in active mode?
Yep. So you can quite literally pull power on any of the racks, and it'll still keep running.
So you're using keep live D to ensure that the virtual IP is on the same machine as the HA proxy?
Yes. Yes. Okay. Anything else? Any other questions?
What sort of data volume increase have you seen from keeping the logs from the old cheat service and the monitoring of the system?
Sorry. Could you repeat the question, please?
So, sorry, I'll phrase it better. So, that volume requirements of the system
Yep.
grows over a long period of time.
Yep.
What kind of smarts do you apply to your customers in being able to kind of keep a lid on that data volume?
Okay, so let's separate between metrics data and log data. Okay, log data is the easy one because you're not really dealing with massive volumes there. The bigger problem is, so first off, the log data, you can trim the log data after however many days. That comes down to the customer's data retention policy. Yes, there are certain organizations where they interpret the regulation to such an extent that once anything is written to disk, it needs to be retained for some number of years. But setting those guys aside, generally you can trim after certain pre-configured number of days. As for metrics data, that's a hard one because you've got massive volumes of metrics. And luckily, for metrics, you're dealing with relatively short-lived data. So what you're looking for is behavior. Behavior patterns, once you are past the 2-3 hour window, you can start to aggregate them. And when you are past the 1 week, that's almost certainly you can start to trim down the older data. Okay? Answer your question?
Yep. How about, just to expand on that, so in that example, again, you've got 150,000 PX.
Yep.
How are you managing that data?
Sorry.
Even if it's like one day's worth.
Yep.
It's going to be a bunch of terabytes.
Yep.
So how often are you trimming that?
Knowing what to ingest and what not to ingest, and knowing what to throw away and what to aggregate before you even ingest into your data store. So by the time it hits your data store, you already have much less data than just taking blindly. Yeah. Okay? So there are certain things that you can do. So for example, if you take let's say cache metrics. Suppose you've detected that a particular process is getting lots of cache miss at certain levels of cache. And we're not talking about just last level of cache. Okay? There are two situations that can cause cache miss. You either have contention between processes, or that process is really dumb. So it's jumping all over the place in memory. The problem is you don't necessarily know upfront by looking at cache miss on itself, by itself, which is it. But when you then look at, okay, what is this process doing in the FP unit? What is this process doing in the integer unit? That's when you can get a little bit more knowledge on, is there a contention or not? Is this a contention problem, or is this a dumb process problem? If it is a dumb process problem, you can't do anything with it. You can't do anything about it. But if it's a contention, Yep, you want to fix that. So that's an example of data that you collect, but you don't necessarily need to ingest. Because you're inferring before you even hit the network. Okay?
It's like a one-time figure or whatever. As in on basically more or target that you want to collect, I guess, is the way you.
Yeah, so the company name, Sardina Systems, comes from the idea of packing VMs like sardines. The founding team came from HPC background, where we were writing high-performance math libraries. In high-performance math libraries, you're taking, essentially, math algorithms, convert to some code that runs on some machine, and you want it to run fast. And in order to do that, you need to understand what the code is doing at execution time. So you profile, and you profile, and you profile. And then you try to adjust the instructions, adjust the timing to eliminate bottlenecks. And so what we've done in relation to resource management is to take that process, what goes on in a programmer's head, turn it into a decision engine. And the data that we are collecting is essentially the data that a developer writing high-performance math libraries collect. And what we're doing for metric collection is basically profiling continuously, the same process over and over again. The benefit here is that we know from the outset that we are profiling one single process, which is KVM. That makes our life a lot simpler. Okay?
How do you do it, like all node in a RabbitMQ cluster or in a MariaDB?
Sorry, repeat, please.
I mean, how do you do if all the node in a RabbitMQ cluster all dies, and how do you recover it? So,
If all of them die, you're in shit.
yeah, I know. Well, ideally, we should keep at least one instance running, but yeah, there's sometimes it all suddenly dies, and you have to choose which one has the latest data. So you choose that to start to bootstrap the cluster again.
Yep.
So similar to the MariaDB cluster.
Yep.
When if at least one instance running, that's okay. You can just start all the
Correct.
others.
Yeah.
Good. But if just shit happens,
Yeah.
if they all died, can you quickly decide which one to start to bootstrap the cluster?
So, MQ, the principle behind MQ is that it's a conveyor belt. So the conveyor belt doesn't necessarily concern itself with what's on the conveyor belt before it went down. So inevitably, you will lose data when you have lost MQ completely, right? Pick one, whichever, it doesn't matter. You've lost data some anyway by that point. So there's no point in trying to pick one or pick a particular one. You've lost data.
they have on disk, they may still have the data.
Sure. But that's a question of which instance has more data at hand. But you know at that point that you would have already lost some data somewhere. So right now, as an operator, your objective isn't necessarily trying to figure out which one has which message. Your objective is to get this thing up now. Get it working again. So with that overriding requirement, you pick one, run. Okay? Right, anything else? Great, thank you.